So, welcome to demonstration video 5 on accessing databases in our short course B07 on using R packages. We'll look at a range of options now for accessing database data from a range of sites, just to give you a sense of how you can do it. And it's quite possible, just depends on what you're precisely looking at. So, an example of this is we can use the package I mentioned before that we can use DevTools. So if we use DevTools, we can use this package by a group called EpiForecast on, for example, COVID regional data. So what this set of packages does, it accesses data from the WHO website on COVID cases and deaths for each country per day across the world. So we can activate that. Oh dear, activate that. Let's activate that. Load dplyr, load DevTools, and scales, which is another required library in there. And what we need to do is set up caching to store this file in our memory. So the file is quite large. So it sets up a local space for the file. We can stop it if you want or reset it. And then we're accessing the data. So the NOTS variable is the variable to which we assign the national data. So you can see there it's actually downloading it. It is 263,000 samples now. It's increasing every day. And it's 15 features for each person. So this is actually wide data, even though it has a lot of rows in there. So we look at the structure of it. So there we have it as things like the date and then cases, deaths, and so on. And in this example, we're looking at Ireland, the UK, and Germany. If you wanted, we could change this to Italy instead. It's whatever countries you want to look at. So let's assign that for X1. So X1 is input here for get national data on the countries. So if we look at, let's say, Ireland only in X1, we'll see that we get that national data for Ireland only from that. So you can see we have the days, the recent days, and then we have the totals for each of these different columns, and it goes right back all the way in time. So that's what we're doing here in line 455. So if we look at the structure of that, we might find it's got 3,033 people in this case. And what we're going to do is plot that as ggplot. So this looks complex. What we're doing is we're basically taking this data and we're plotting it out as ggplot. So if we do this, we basically create on its own an empty canvas. So line 457. So this is our canvas, and we can map onto this aesthetics using X and Y, where you have the date and the deaths per country. So we just do dates and deaths only. We just have a basic plot created here. I think we need actually more data for it to plot fully. Okay, let's see if I do the whole thing. Okay, it's not plotting right now. So if in doubt, if you get stuck in plotting, just hit dev.off and see what happens. So let's go back to where we were before. If we just want to plot the deaths and cases over time, we'll have a basic plots like that. And then we can add in the country as well onto this kind of background. And then we can add in a geometric line indicating the pattern that's present. So you can see now we have the pattern per country. We might want to change the labels to be date and reported COVID deaths with the theme minimal. So we tried the theme minimal alone on the previous one. We get a similar plot, but less annoying colors. And then we can modify it. So we can put the legend position to be the top. Let's try that. There, that's maybe easier. We can add on the title as well. And what else is it doing? It's scaling the y-axis to be continuous. So you can see there, we have a continuous data there. And yeah, so that's what our plot is doing. We can change the countries. We have Ireland, Italy, and the UK here. You can change that to whatever you want. So if we want Ireland only, we can just repeat that for Ireland only and plot that out for Ireland only. We don't have to, we can toggle all sorts of these features depending if we want a particular date range or whatever. So you can see there's a big recent spike in Ireland. So that's one example of accessing large-scale data that we can then plot. Another example is viral sequences. So in this instance, what we're going to do is look at viral sequences using Sequenor and APE that we had before. And we just have, say you have a bunch of accession numbers and you want the sequence data for them. The thing to do is to put them in a vector called list1 here. So these are just example. These are partial VP1 sequences from foot and mouth disease virus for SAT2. So we can put them in a list, and these are query sequences. So what we want to do then is basically query them with a website, and there's a variety of tools to do that. One handy function that's in Sequenor is read.genbank. So if you look at Sequenor, if you look at read.genbank, it will just take in a list of accession numbers, and it will ask for the sequence names. So it has the seq.names is the same thing. We want the species name just to be sure, and we're treating it as a character output. So if you perform this and check the structure, what we'll see is that we get the sequence data for each of these samples. So let's look at seqs dollar. We'll choose the first one. You can see there we have the sequence for that sequence, and then there's metadata embedded in our vector there. So we can check the attributes of our species as well. They're all foot-and-mouth disease virus, SAT2. And then we can write that out if you want. So it's a special function, write.dna as a FASTA file. Format FASTA, append equals false. You can toggle to say you want a column separator for any bizarre reason. You can do that, but you're best off leaving it as these defaults, which is just write a straightforward FASTA file only. So what we can do with that is further things. We can, just like we did earlier, we can we'll align them with we're aligning the muscle here. You can see it aligns very quickly because they're very small, just 648 or so bases. We can check the alignment. There's high identity there, but there are some sites that vary. We can convert it to a Sequenor object to construct a distance matrix. We can view that matrix to see how different they are. There's a lot of variation there. You can see straight away. And plot out phylogeny. So there we have a phylogeny showing each of the sequences. So you can see that some are more similar and some are not. And then if you're good, you can add a scale bar in the location, but that's a bit fiddly. So I'll leave that to you to add the substitutions per site to denote the information inside the horizontal branch links. Another example is querying text to databases. So say you want all the foot and mouth disease virus sequences in the nucleotide database. You can do that as well. So what you can do is install the Rentrée package, which allows queries to Entrée, which is very convenient. What we're doing is an Entrée search using the nucleotide database. If you see on the website, it's actually called Nucore there. And this is our search term. It's like searching text. It's the same thing. We just have to make sure we spell it right. And then we're just talking here to return a maximum of basically infinite sequences because we just want to see what's there. So if we do that, search one, and you can see there, it's going to search them all, and it's done it in second, and it has downloaded 14,516 foot and mouth disease sequences in seconds. So it's very, very quick for downloading large scale data. And then you can ask, okay, what are my NCP IDs for all these sequences, and that'll print them out there. So then you can use these IDs to query them further. So we have an example there where we're using RDs for Entree fetch to fetch the sequences. So it's one to access the accession numbers. It's the first step. Query, get our accession numbers, then get the FASTA after that. So what we're doing there, search IDs, the FASTA, and with the database. So we get that, put that in the seeks for. And what do we have now? The quest is too large. Anyway, you're probably not going to do this because if you look search for the organism only, you get all the sequences, but there doesn't mean the sequences are actually related to each other. But this is just for illustration. So you can see that we're able to get sequences and then we can write these to file. What we would want to do in reality is to use a Boolean inside our search term. So we're saying and is a Boolean when you're querying a database. So we can use that. We can say and the BP1 gene. So that will give us the BP1 gene sequences available for foot mouth in the nucleotide database, all of them that are available in seconds. So we get 153 on this database. Obviously, there are other databases. I'm not saying this is the place to get them for all organisms. But we get a bunch of IDs and we can use these IDs then to extract the FASTA file as we did before. We can check what we got and then we can write it out. And then we can repeat our distance matrix and phylogeny construction task we did before from seeks 5 in the same way, using the same code even. So you have to align the sequences. Here we're using Clustal Amiga because muscle may not deal with missing data well. So may give an error. So just bear that in mind. And then we have my A5 is done. Next step, distance alignment. So that's our distance matrix. So put that in plot.philo to plot our tree. And then we get our phylogram of the 153 VP1 regions for further evaluation. So we'd have to go back to the metadata to really understand what's going on. And you can toggle the tree shape as you did before. You can play around with that. I try to add a scale bar, but note that that will map coordinates onto the image, which sometimes don't always appear. So it can be quite confusing. Finally, our last part, we're going to look at a FASTQ file. So there's an existing FASTQ file in the N drive. And we're going to use these two packages, ggplot and shortread. Shortread is the main one we're going to use here, and we're going to plot stuff with ggplot. So you get that FASTQ file from the N drive. It's in the Omics Learning B07 folder. It just contains 1,000 lines from the top of a FASTQ file. Therefore, it just has 250 reads only. So each line just has the sequencing information, the DNA bases, their quality scores, and then a divider. So 4 lines per read. So we can read that in just using the function read FASTQ from shortread. So if we read that in, that saves as a kind of a FASTQ object. We can check the structure to make sure that it worked. And we have 250 items in there. And now what we're doing is we're going to use the special function quality to extract the quality scores from the FASTQ file. So this is a special kind of command matrix to compute a matrix from it. So we're getting the quality scores from that file, putting them in there. So if you check, maybe yeah, you can see there we actually have the quality scores already inside there for each of them. We can draw a quick histogram even now. What we're going to do is get the row means for each of these and code that as a data frame on the next line so that we get the average scores for each of these. Yeah, X is not numeric here. So hist average score. There, you can see there. even now. There's definitely a difference here, but we can use ggplot to look at it properly. If you do ggplot average score only, this is kind of our blank canvas. And then what we're saying here is GM histogram to plot the x-axis contains the average score. So adding that on top of our blank page. Oh. So let's run through that again. So let's revert to histogram. Plan B. Let's change the number of breaks to be how many? 40, 50, 50. And then what else do we want to do? We want to add a grid just so you can see it more easily. Again, I made the same mistake. So we're just using the $sign to extract the column. There we go. This is basically what I was going to show you in ggplot. So you see this quality scores in the x-axis going from 18, 17 up to 40. So we can change that actually. There we go. That's more easy to read. 15 up to 40, yeah, but 18 all the way up. I can see the frequency of the different reads and check their quality scores. So obviously we want to select the ones that really have a higher quality score. And you see there's actually a lot of reads there that do have quality scores. So getting rid of these crappy reads is probably a worthwhile idea. We'd also want to do it on a per base basis as well. So this is just an illustration of how you can look at WHO data, large text files from websites. You can query accession numbers using R. You can use search terms and query databases using R. And finally, you can look at FASTQ files using R. So there's a huge amount of things you can do. And this is just a quick taster of 20 ways of accessing database data. So that concludes this video.